Bill for the introduction, and also it's amazing that there are great effort from AI camp to populate AI work to everywhere across the world. Yeah, and I think this is also quite a promising area, and also very respectful for this effort to help everyone get into this area and contribute to the world. At LinkedIn, we also have a word like AI is the oxygen. So we hand over like using AI everywhere into the product in different teams to help power our features for online member experience improvement. Yeah. So back to today's topic. Thanks everyone for your attention, for your time. Let me put it to the full screen. Okay. Yeah. So I'm Huiji, together with my colleagues Xiaowei, Sida, and Weiwei. We are from LinkedIn, and today we are going to present this topic, DeText, a framework for deep natural language processing at LinkedIn. This work, DeText itself, has already been open sourced, and we also have a set of publications related to the work done by DeText towards industry applications. The most recent one is CICM actually. So this week, we are also going to present some of the work at CICM. And if you have a time, feel free to stop by. You can also search DeText LinkedIn in Google, and you will easily find the open source page. Okay, we are going to cover more details later. A brief introduction to myself, probably. I'm currently a senior manager at LinkedIn, managing the AI algorithm foundation team. So the team works on a set of components in search and recommender systems. These components including the deep natural language processing, ranking personalization, deep reinforcement learning, model selection, and so on. Yeah. So today we are going to cover the deep NLP part, which is DeText. In today's talk, we are going to first introduce NLP in a search recommender system ecosystem. And then we are going to discuss the deep natural language processing. After that, we will formally introduce the DeText framework, followed by its applications in ranking, classification, and language generation. Then we are going to conclude the work. First, let's take a look at. I want to introduce the commonest ecosystem in our online industry. That is search and recommender systems. And just to take a quick poll, have anyone used, I would say not used, search recommender system in last week? Just raise your hand. You can do a virtual hand raising right, in Zoom. I probably cannot see, but I believe not a lot, right? I think almost everyone has used the search and recommender system either daily or pretty frequent in your lifetime. So this is almost everywhere. And these systems, they have different functionality. Users would like to obtain information from these systems for different purpose. For example, we look for people. We can use this system to look for jobs, look for content, look for restaurants, look for videos, and look for traveling tips. Now, how does this system look like? Right, let's take a high-level look. The first one, I want to introduce search systems. On left side, this is a screenshot from a LinkedIn job search. On the right side, you can see a high-level structure of search systems. Usually, we have two types of input. One is a raw query inputted by user. Another is a set of documents that usually the system want to match to this query. So for both two types of input, we need to understand their content. Right? For query, we have query understanding, and for document, we would have document understanding. After that, the system will start to do document retrieval, trying to find as more relevant documents as possible and sending to the ranking component to further improve the ranking precision. Now, this is a typical search system. And here are some examples. Also, we are using LinkedIn's system as an example. This is for people search, and this is for job search, looking for jobs, and this is for content search. There are more, but we are just list a few to give a high-level sense. Now let's take a look at recommender systems. Yeah, again, on the left side, this is a screenshot for job recommendation at LinkedIn. And typically on right side, this is the high-level structure. You see that in recommender systems, we no longer have user queries, but instead we have user profiles. And we try to understand the user profile, then trying to match relevant documents to this user. And this process, again, follows the document retrieval, then followed by the ranking. Yeah. Now, with this brief introduction, can you tell what's the major difference between search and recommender systems? Ideally, it seems that this is the only part, right? One, in search, we have the user query, and in the recommender system, we have the user profile. But fundamentally, how these two systems work are dramatically different. In search systems, it is more like an active mode. Now, user trying to give the system a query and then pull information to get what they want. But in recommender systems, there's no such query. The system trying to understand the user and trying to push information to the user side. So this is more like a passive mode. That is actually the major difference. And if you look at some examples here, you see that this is a people recommendation at LinkedIn. You can recommend people to user, and this is job recommendation. This is content recommendation. Now, with all these information together, we can merge them, and we can represent search or recommender system with this unified high-level structure. Right. On top of that, there are information from user, either the raw query or user profile, or sometimes both in search systems. And there are also documents, usually generated by many other users. For each of the components, we want to do understanding, from query understanding to user understanding to document understanding. And then we do document retrieval. Retrieval usually trying to improve the recall. That is trying to incorporate most of the relevant documents, right, by excluding irrelevant documents as much as possible. Right? And then passing this to the downstream ranking to do a fine-grained work to help improve the ranking precision. This is more like a generic framework, and it can be applied to either a search system or recommender system, depends on what kind of input information is available. But you may still wonder, like, how would this be relevant to today's talk, right? We are going to talk about NLP. Now, let's take a look at take a deep look at the ecosystem on that. Again, we have search and recommendation. So I'm just going to use the LinkedIn search ecosystem as an example, but this can be generally generalized to many other different systems. Let's say we have search and recommender systems. Now in search, as we mentioned, usually we have a raw query. Recommendation, we usually count on the member profile because there's no query. So with the query information in search, typically we can do a lot of online assistance for the user. For example, we can do spell check to help user correct their spelling errors in the raw query. We can do query suggestion to suggest new queries to the user. For example, user types software engineer, and we can also suggest a software developer. There are also autocomplete, help user to automatically complete their query. Say if the user types soft, and we are going to, the system is going to automatically complete the query to software engineer. Now, these are online assistants starting from an input raw query. And now, once we get this raw information from the user, now we need to do some fundamental text processing. Typically, this includes the language detection, the tokenization, and the normalization accent handling. Now, after all this is done, now it's the time for us to understand what the user really wants. user intention understanding is one of the most critical part here. In search, because we have the query, now this topic usually refers to the query understanding and the typical components including query tagging and query intention. Using query tagging as an example, this is more about understanding the name entities in a query. Say we have a query about a software engineer, Huiji LinkedIn, and the system want to know that software engineer is about some kind of job title or skill. Huiji is a name and LinkedIn is a company. And this is for ease of downstream ranking and retrieval. Now, query intention is also used in many places, especially in when you have a branded search engine. It contains different types of entities for user to fetch, right? So when user type software engineer, you may want to understand, is this user looking for news about this topic, or looking for people, or looking for job, or looking for video? This will refer to the query intention. And on the recommendation side, on this channel, right, on the recommendation side, we usually use to understand the profile and the behavior from the user. Okay, now let's say we understand the user intent. Then next step is trying to fetch a set of candidates, right? These candidates could be relatively large, but as long as downstream ranking can handle, and as long as it covers a good record, contains most of the relevant documents. So inevitably, it will be working together with the document understanding. And also document understanding needed to go through the text processing process. In this stage, usually in search, we refer this process to be retrieval. And in recommendation, we refer to as targeting. Now, after that, we are conducting ranking, right? With this candidate set from candidate selection, we are going to do a ranking to improve the relevance, to improve the precision. Right? This will also consider both user input, raw query, member profile, and the document pool. Now, from this whole process, you probably already get a sense that text data is almost everywhere, right? From the query, text data can be used for online assistant. It will be used for text processing, used for user intent understanding, used for candidate selection, and even for document ranking. So NLP is playing a crucial role in search and recommendation systems. It embeds almost into every component into this ecosystem and can power different functionalities from top to down in the system. Right? And today, we are also going to talk a bit deeper. We are going to talk about deep NLP, how to use deep learning to develop NLP technologies to power search and recommendation systems. Now, so far, I think you probably will get a high-level sense about where NLP is used in this system and which are the different components that NLP can power. But you may also wonder how we can develop such NLP technology and how this can make an impact from different perspectives, especially why do we need deep learning, right? These are the questions leading to the next session, deep natural language processing. And with that, I'm going to hand on to my colleague, Wei Guo. Yeah. Also, before that, is there any questions so far?
I think there are a couple of questions in the Q&A. If you can quickly go over
let me take a quick look. Q&A. I probably can stop share. The first question is, does DeText assist with many of the things you mentioned in your site on search and recommender system? Text processing, intent understanding, and the answer is yes, yeah. We are going to introduce in the next session deep NLP, and we are going to give you a big picture about how deep NLP tasks are classified to fit into this search recommendation system search recommendation ecosystem. Yeah. The second question is, can you explain a bit more about extracting job role from the raw query? What's the model? Is it open source? Oh, yeah. So in the third session, when we introduce DeText, we are going to talk about how to use DeText for ranking, end-to-end ranking, starting from a job query, and then eventually provide a good ranking list of jobs to this query. So probably we can provide more details to this question at that time. The third question, how did the search recommendation engine share the components being used in LinkedIn? Oh, yeah. So from the ecosystem, you pretty much can see, right? I cannot speak for too much details in LinkedIn, but I can share how this usually is designed in the industry, right? So the shared components, including first of all, index, right? You anyway need some place to store all the documents and to index them. So this is a shared component, and depends on the use case. Some of the application want to separate them. Some of them would like to couple them. And there are pros and cons, right? For example, if you couple them, that means like you have multiple systems relying on one index, which sometimes will be a bit low efficient. And if you separate them, of course, there will be some information async issue, right? And ranking, right? You can see that for search, because user has query and the result is limited to a set of documents specifically to this query intent. So learning to rank is usually used. And for recommendation, usually we use point-wise ranking algorithm because people maybe cares more about the absolute relevance score. These are some details we can always discuss later once we have introduced the DeText. So, but in terms of technology, the ranking algorithm can be generically used for both search and recommendation. As you can see, DeText is this example. Yeah, I hope I answered the question. Yeah. It's maybe a bit high level since we haven't introduced the details to DeText yet. Yeah, but feel free to still type your question. I'm happy to answer. Great. If there's no questions, then I'm hand on to Wei Wei. He is going to introduce deep learning for NLP. Quite exciting area.
Hi everyone. So so you can see my screen, right? So thanks Huiji for the great introduction of the search and recommender system. I'm Wei Wei. I'm the manager of NLP group in LinkedIn inside Huiji's group. So I will talk about the deep learning based natural language processing in an overview, and then I'll hand over to Xiaowei and Sida for the detailed design of the DeText framework.
Sorry, we're seeing a empty Google page. Not
an empty. Okay.
Yeah.
Let me check.
Actually, I can see the page.
Yeah. Right now we can see the slides.
Now it's good.
Yeah.
Now it's good. Okay. So as Huiji just explained, the natural language processing is a key component in the search and recommender system. So on one side, we have the users, and on the other side, we have the computers, and then they are interacted with the natural language data. For example, the human can generate a query, and then the search system needs to understand the query and retrieve the document. So this part is usually called natural language understanding components, NLU. On the other side, the computer can also generate natural language data, such as the spell check or query suggestion by generating a better query. And then this is to assist the search and recommender task of the human. And this part is called natural language generation. So I would like to talk about the difference between the classical NLP and the deep learning based NLP. So in the classical NLP is usually a very long pipeline. So given a document, you need to detect the language. And for each language, English, Spanish, Arabic, you need to do some language dependent pre-processing, such as tokenization, POS tagging. And then For each language, you need to do individual modeling, extracting the features, build the models, and do the inference. And you have to do this for each of the tasks. So as you can see on the last column, you have many tasks such as sentiment classification, entity extraction. So things are simpler on the deep learning side. So for deep learning side, also need to maybe do some language and multitask. Multilingual means that you build one model for all the languages. And multitask means that you generate a lot of features that can use for that can be shared in many tasks. So in the last slide, you can see there are a lot of NLP tasks, but actually we can summarize it into several representative tasks. And in these slides, I will talk about the representative task and the correlation between them. So when you do a deep learning model, at the core of it is the sequential modeling, which means that you use CNN or LSTM or transformer to generate word embeddings and sentence embeddings. And then by adding different loss functions, you get different tasks. For example, when you add the sentence level label, it's a classification task. An example is the intention model. When you search a query at LinkedIn, are you searching for member profile or are you searching for job posting? And then you can also add a loss function to each of the word. It becomes the sequential tagging. An example is a name entity recognition. So given a query like software engineer LinkedIn, you want to identify software engineer is a job title, and then LinkedIn is a company. Also from partial sentence, you can extend it to complete sentence, such as query autocomplete. And given one query, you can generate a better query suggestion by using the encoder-decoder framework. So that is from one sentence to the next sentence. And after that, you can do the document ranking. So as you can see here, the left side two tasks are the natural language understanding task. And on the right side is the natural language generation task. And then the ranking is the matching task. So these are the 5 representative tasks. And also we have one task that can boost the performance of all the tasks. That is the unsupervised representation learning. So recently the BERT pre-training has been proven very useful for many of the NLP tasks. So our DeText framework currently it supports the neural ranking, the classification task like query intention, and then the query autocomplete. So this also answers some of the previous question. What does DeText support now? Our goal is to support all of the 6 representation tasks. So now we have a look at the representation task. Now we can look at the data. So as you can see just now, all the search and recommender systems are trained on the queries, the user profiles for personalization, and then the document, which is the target of the ranking. In order to build a strong search and recommender system, you need to understand the text semantics very well. So the challenge of the text semantics, here I summarize 3 ones. The first one is we need to identify similar meanings. Software engineer is similar to programmer. And also we need to perform word sense disambiguation. So restaurant opening is a skill, while job opening is highly related to job search intent. And then we also need to identify the most important words in the query or in the profile. For example, here only the software engineers are the most important words. We cannot use the looking or job to do the document retrieval. So there are many benefits of the deep learning based NLP. One is that it can solve the deep semantics for the text, as I mentioned in last slide. And then it can also do automatic feature engineering. All the features are machine learned. It is end-to-end modeling, meaning that all the parameters are jointly optimized. For example, in the recommender system, it is to optimize the clicked document. And as you will see later, it's very flexible to replace one module in the DeText framework. So here we provide multiple, for example, we provide multiple text encoding methods such as LSTM, CAN, and BERT. So our goal is to design the DeText deep NLP framework. So what are the challenges? The first one is we have very different requirements from each task. The input data is very different. And also the last function. For example, the search system needs a list-wise learning to rank, while the recommender systems uses point-wise learning to rank. And also we need to balance well between the effectiveness and the online latency. The production models, which is the traditional NLP models, are actually very strong and robust because we have iterated many times and designed very powerful handcrafted features. So the deep learning models needs to be computationally cheap, and also it needs to beat the production model. At last, usually the search and recommender system are trained on millions of or even billions of data points. So we need to, the offline training needs to be fast in order to allow, for example, hyperparameter tuning. So these are the major challenge we are facing. With that, I will hand over to Xiaowei and Star for the detailed design of the DeText framework. So now let's look at what are the questions we have. The first question is, can you explain the difference between NLP, natural language generation, and natural language understanding? So usually NLP equals to natural language understanding and natural language generation. And natural language understanding focus on extracting the semantics or meanings from the original text. But natural language generation will generate new pieces of text. The other question is, what tools or components do you use to the degree of understandability or readability of text, chunk text from some to high? So I'm not sure what does it mean to detect the degree of understandability of readability of text. So in your case, it seems if we want to detect a John text from reasonable text, I think classification will be the right solution to it. So you just label some of the text as junk text and some of them as readable text. But I guess also you want to use it in an unsupervised way without labels. Currently, I cannot think of any ways to do that. The third question is, it keeps changing. Can you tell me more about automatic and manual feature engineering in text data? What tools or pre-processing or techniques you can share with us, frameworks or libraries? So, so for feature engineering, the traditional methods actually do a lot of, the features are like a back of words feature. So back of words feature, you can think of it as a unigram feature. So it means that it's a sparse feature, whether my text has the word job or not. If it has the keyword job, it's 1. Otherwise, it's 0. So these are the, and then we may have a very large vocabulary, meaning that most of the features are sparse. For automatic feature engineering, basically you just use deep learning approach, and then you will see in the later slides.
Yeah. So yeah, just to add one comment. I think you are looking for framework or tools to help doing NLP work, and DeText is such a framework. So maybe after the introduction to DeText, you will get a better idea how it does. Yeah. So far, I think we are still describing very high level, so you may not easily present this sense to you yet.
Yes. Yeah. So so for other common, I think, for example, language dependent processing tools, or if you want to just extract some common linguistic information, such as part of speech. So Open NLP has a lot of part of speech extraction tools. The next question is, how do you handle the false positive and false negative in name entity detection of the job role? What's the approach? So currently we are developing the name entity recognition approach inside DeText. So it will be available maybe next year. So I can give you a high level of what are the false positive and false negative. So basically in the name entity recognition, you annotate each word. So it's like you are doing classification on each word. And then, so you imagine you are doing logistic regression on each word. So for the false positive and false negative, they're actually already handled by the logistic regression algorithm. But in fact, more advanced techniques are conditional random field. So basically it means that when I predict in the current word, I need to know the previous word's classification result. By doing this, we can significantly improve the performance. The next question is from Veer. How do you define the predefined labels, such as software engineer is a job while person is a person search? So we'll use click-through data, and Xiaowei will explain it in detail because she has an example of the query intent classification. The next one, can you provide the link to get more resources on the web? Sure. So
I just typed the link.
Okay, great.
Let me also post this in our journal chat so everyone can access the GitHub.
Yeah. Okay, the next question, say I have a data set with text data. Each row has a line or multiple lines of text, single line. What tools do you use pre-processing? Analyze such data. So what do you mean by analyzing? Or so we use a lot of large-scale distributed tools like Pig or Scala to analyze this text. Do you have any other thing to add, Sida, Xiaowei, or Huiji?
Excuse me. I see we have quite a lot of questions. Do you want to keep moving to the next presentation? And then maybe we can come back to answer all of the questions.
Yeah, sure. I think
some more questions maybe make more sense later on when we introduce the DeText.
Yes. Okay. Xiaowei, maybe you can share your screen.
Sure. Let me share. Oops. Okay, so hi everyone, my name is Xiaowei and I'm also from the NLP team at LinkedIn. So I will continue to introduce the DeText framework, also including some of the applications in the next following slides. So, so the team developed DeText with several goals in mind. First, we want to provide the state-of-the-art language understanding and also language generation from text data. And also will be an end-to-end framework. And also has to be flexible enough for the different tasks that we just previously mentioned, including ranking, classification, and also language generation. So our framework is called DeText, which we hope that users can just relax like a sloth, like in our icon, and then let DeText do the understanding for you. And here's our most recent edition of the logo. So I'll next talk about the detailed design for the DeText framework so that you will have a better understanding for how you can design a model using the DeText. So in the very beginning, so in the input, you have a bunch of raw text data that you can use. So you can have multiple fields. For example, you can have query, user profile for the source field. And then for the target fields, the text data that you want to match, for example, in the document, you can also have multiple of such fields. And we're going to look at some of the examples that we mentioned with a more concrete understanding for what are these fields can be. So after you extract the raw text data from your data set, we can add a word embedding layer to map the raw text tokens into a word embedding matrix. And after that, since we provide different type of deep learning modules that you can use as text encoders to generate the text embedding vectors, you can choose from CNN, LSTM, as well as BERT. And after that, basically we've learned the representation for each of these text fields that results in these multiple text embedding vectors. Then we're going to add a interaction layer, where by interaction, we just mean we're going to compute some sort of interaction functions from the source and the target fields. And some of these can be, for example, the cosine similarity, Hadamard product, and things like that. And because a lot of the production systems already include a lot of the very powerful handcrafted traditional features, we also include them in a sort of deep and wide fashion through feature normalization. So basically just concatenate those features to our deep features. And followed by that is our MLP layer, where you could have multiple such like fully connected hidden layers. And for ranking, we're going to compute a target score for each of the target that we want to rank. And of course, you're gonna have multiple of these scores for all the target or documents. And then finally, for training, we're going to compute the learning to rank loss, which we call the learning to rank layer. And since we're also dealing with like classification, This can also be swapped to using a multi-class classification loss to deal with the classification tasks. So that's the overview for the DeText framework. And we also want to call out that throughout the entire framework, users have the very high flexibility for customizing the model into their specific tasks. So for example, at the very first layer, you can configure the input fields to fit your tasks. For example, you can have query user fields, document fields, and you can have basically arbitrary number of such fields. And also you have the flexibility to choose from the different deep modules from CNN, LSTM, and BERT. And for interaction layer, there are also multiple of them available. For example, the cosine similarity. You can also simply concatenate all of the embeddings together and compute the differences, etc. So we have a lot of them for you to choose from, and you can use a combination of them too. And so again, traditional features will be added or can be added in a deep and wide fashion. And for the task-specific losses, we also provide a lot of them. So for ranking, you have the point-wise, pair-wise, and list-wise loss. For classification, we also have the multi-class classification loss. And similarly, you can choose from the different optimization algorithms we provide, including the support for Atom SGD, the BERT optimizers like the Atom weight decay and also LAM. And for metrics, users can also choose the corresponding metrics for their specific task. For example, NDCG was ranking, AUC was classification. And also throughout the entire design of the framework, things like number of layers, layer sizes, the filter window size for CNN, those things can all be are all configurable when you're designing the DeText framework. So in the next slides, we will be talking about introducing the some of the typical applications that users can design using the DeText framework. So I will talk about 2 natural language understanding tasks, including ranking and classification. And after that, I will continue with the natural language generation application. Let's first take a look at ranking. So as Huidi and Weiwei previously mentioned, search is very popular, very important product in modern search and recommender systems. So you can see, so at LinkedIn, we have like people search, job search, and also content search and other search verticals. All of these include a large amount of text data that we can utilize. So we will take job search as an example to see how we can build a job search ranking model using DeText. So for job search ranking, the user input will be the query. And then the documents that we want to rank include is the job post. And then we can extract the different fields from the job post, including the job title and job company. And of course, you can also extract, for example, job descriptions and also other aspects from the job post. But we're just going to use these 2 for this example. So for a job search, we have a query and also, for example, we have a document here. And then we can extract the raw text from the query and also the job title and job company. And remember, we can add the text encoder of your choice to extract the text embeddings from these text fields to learn the representation. And then after that, we can have a interaction layer to compute the similarity between the query and those 2 document fields. And after that, because the job search ranking is also a very mature product, we also add those dense features, like the traditional features, through feature normalization to these deep features. And followed by that, we add some hidden layers. And then for ranking, we compute the listwise ranking loss. So that is basically how we can design a search ranking model using DeText. And notice it's very easy to change from job search ranking to a different type of search ranking. Basically, you will just have like a different type of input. For example, you can have query, and then you can have the member profile text fields to fit this model into a people search model. And yeah, so at LinkedIn, we have been doing a lot of experiments using DeText on different search verticals, including job search, people search, and help center search. And we have shown here that through offline and online experiments, these deep models, including DeText CNN and also DeText like BERT related models, all achieve a very significant improvement. And so we also want to call out some of the like challenges that we've seen during the development of these ranking models. So because essentially we want these deep models to be able to ramp to production for real-time online inference. So there are definitely a lot of challenges related to the model size and also the latency of serving. So we're gonna talk about that in the following slides. So the very first is a general challenge for these deep ranking models, that because they have a large number of documents to rank. And then for real-time inference, these computation costs grows linearly with the number of documents. And another challenge comes with using BERT for serving. This could be like almost 30 times slower than CNN when we're using a Google BERT, the Google's BERT-based model, which has like over 100 million parameters. So this significant increase in the latency definitely is a very big challenge for putting these models in online production systems. So we're going to look at the techniques or the methods that we took to overcome or alleviate these two challenges. So the first one, to solve the latency that relates to the large number of documents, we adopt a two-pass ranking scheme. That just basically means we will have two layers of ranking models for this production model. And then for the very first layer, we're going to use a very simple model that has the ability to return the results very fast. So for example, we use a NLP model with just the traditional features without any like deep modules. And after the first pass ranking, we can retrieve the top, for example, the top 200 docs in this case. And then we apply the second pass ranking just on these top documents. So, and then also in the second pass ranking, we'll use the deep models that we previously defined. So in this way, we're going to see a decrease in the latency for these online models. And to tackle with the other challenge that we mentioned related to BERT serving, we have two major solutions to this. The first one is related to the BERT model structure. And so we introduced LIBERT, which is the LinkedIn pre-trained BERT model. That's a general BERT model that uses the same like BERT model structure, but with a more concise design. And it's also trained on LinkedIn text data, because we expect that with pre-trained like in-domain pre-trained BERT models, it is going to be giving us a better relevance. So let's take a look at the LIBERT model latency performance. So we train LIBERT models with a slight concise architecture compared to the Google's BERT-based model. So you can see we take an example of the LIBERT 6-layer model compared to the BERT-based model. And we use, of course, we use 6-layer of transformer layers. And then we also reduce the hidden layer dimension to 512 compared to 768. So that results in about 1/3 of the total number of parameters compared to the Google's BERT model. So that gives us a reduction in latency in about 30%. And notice that we also have other, even like tinier models than the 6-layer model, where we have like a 3-layer LIBERT model. So latency will be more reduced in that case. So you may ask the question, even though we reduce the latency by a lot, how about the relevance performance? So let's see, by pre-training the BERT models using the LinkedIn like in-domain text data, we can definitely see a improvement in performance on LinkedIn specific tasks fine-tuned with the LIBERT model compared to the same tasks fine-tuned with the BERT-based model. So you can see in all of those 3 different search ranking cases, the LIBERT model perform better than the Google's BERT-based model. So that is one, so LIBERT is one of the solutions that we took for tackling the BERT serving latency problem. So another BERT serving solution to this latency problem is that we adopt a embedding pre-computation approach. So even though LIBERT models are much faster than the Google's BERT-based model, it is still a heavy model, and putting those models for direct, like real-time inference definitely does not meet the production requirement. So we, because we are learning these representation for the different text fields, we're able to do the embedding pre-computation, because the document texts are relatively static compared to, for example, the queries. That just means they don't really change that frequently. So we can pre-compute these embeddings beforehand and then push them to online key value stores. So during online, the DeText model will take the queries and also the document IDs to retrieve those document embeddings from the key value stores. So that saves the computation cost and just replaced by the network communication cost. So as a result, so you can see in this table, by doing document pre-computation, it definitely brings down the BERT model serving latency time to about this similar, even a little bit less than the DeText CNN model for like all decoding. And another comparison is that when doing the 2-pass ranking, so if you compare the first 2 rows, when doing the 2-pass ranking, it is the latency is much reduced compared to when we do all encoding for the CNN case. And also with the LIBERT DeText model, it is much faster than when using the Google's BERT-based DeText model. So that is the techniques that we took to resolve the challenges that we met. So to recap, to overcome the general challenge for a large number of documents in ranking, we adopt the 2-pass ranking scheme. And then to solve the challenges for BERT model serving, we have our in-house designed LIBERT models that's faster and also has a better relevance performance. And besides LIBERT, we also adopt the document embedding pre-computation for these ranking tasks. So that is pretty much it for the ranking application. And I'll next talk about a classification application that's also using DeText to design. So a lot of these text classification algorithm applications are very popular in like modern search and recommender engines, including like query classification to detect the intent, and also like spam detection and sentiment analysis. So we will take the query classification as an example to illustrate how we can design a DeText model for that. So our input here is the query text and also some other dense features that's also available in previous production. So some of these dense features could be some personalization features, for example, the user's like footprint features, like search behavior features, things like that. And then our goal is to predict the search intents over the different search verticals that we have at LinkedIn, for example, people, job, content, etc. So let's take a look at the model architecture that we designed. So similar as before, we can extract the raw text from the search query, and then we can add our choice of the text encoder to extract the deep features. And we include the dense features or like the personalization features through the feature normalization. And we add some hidden layers on top of that. And finally, a softmax, like a classification layer. And then for like training, we compute the softmax cross entropy loss for the multi-class classification. And notice that because for DeText, you can have multiple text fields, so it is easy to have the ability to add multiple text fields. And what's more important, you can have like interactions among these text fields. So that is how we can design a multi-class classification with DeText. And same as the ranking problem, we also saw significant improvement in offline accuracy as well as online with the member experience and search experience related metrics. And that is for both the DeText CNN model and also the DeText LIBERT model. So that concludes our application for ranking and classification. So the next session, Sida will talk about a language generation task, and followed by the rest of the presentation. So guess I'll stop share. So do we want to answer all of the questions maybe at the end of the presentation?
Maybe you can go over some of them,
Sure.
and then we move on to the next one.
Sure. So let me take a look. I think the first one was from before. So say, can you, from Louis, so can you elaborate more on the algorithm used in the interaction layer? Are you looking for similarities between text? Yes, so to answer your question, that is basically what the interaction layer is about. So you can actually choose from the different types of interaction functions that we provide at LinkedIn. For example, if you choose cosine, then it'll compute the cosine similarity between the two vectors, the embedding, the two text embeddings. And then besides cosine, we also provide many more interaction features, such as you can compute the Hadamard product of these two vectors. You can also just simply concatenate these text embeddings. So that's answered. And another question is, so LIBERT is trained with LinkedIn data. How does LinkedIn data look like? In data points, can you give examples for LinkedIn text? Sure. So LIBERT data, when we designed the data set for pre-training LIBERT models, we wanted to be very general, like general enough for all the type of applications that we have at LinkedIn. For example, it should include job post data. It could also include the member profile text data. So an example would be we can extract the job title and job descriptions from the job post, and all of those tags will be used for LIBERT data pre-training. And we also include other fields like search queries, ads descriptions, and also contents. So it's very general data set. And another question, how do you use different text representations? Do you each have a different purpose or are combined to solve the same task? So, well, you see in the DeText framework, these representations are learned and then it's all trained together end to end for that specific task that we designed. So I think the answer is yes, those are combined to solve the same task. Let's see, do you handle the concat of deep features and traditional features? For example, dimension is 10, 12, and you need to combine it with single traditional features, which are scalars from the traditional features. So I think, so the answer is that we do not really control the number of traditional features to add, and basically you can add actual number of them. But in terms of your concern, I think it depends on the different applications. And so after the concatenation, we always add a hidden layer to learn the interaction also between the deep features and the traditional features. So I think that definitely needs is more like specific to different tasks, and it's worth doing like experiments to see whether that adding that single traditional features help. So another question, real-time lookup, especially using heavy models like BERT, can be quite costly. Does CSAT offer potential solutions to this issue? Do you have any outside framework? Yeah, so so I think this is partly also answered in our slides. So we adopt a embedding pre-computation scheme, and then we save all of those embeddings in a key value store. So then that also depends on the framework that you use. So DeText does not provide solutions to such key value store because usually that's more specific to the online production, but the idea can be adopted because a lot of the times the communication cost for inferencing with the BERT model in real time is much like larger than just looking it up in a key value store. And another question, can we use custom model or models from Hugging Face, such as the Dilbert? So I think the answer is yes, we can definitely use custom models from other places as long as the format is compatible with DeText. So currently we use the checkpoints for initializing BERT models from other sources. So as long as the format is compatible, then we can use those models in DeText.
Yeah, I think to add this question, we are also refactoring the code so that the user can use any model in the TF Hub. Yeah.
So that will be made available after our refactor in the open source GitHub page.
Yeah. So maybe Sda, you can start your presentation, and then we can answer the questions offline.
Yeah.
By typing. Yeah.
Sure. All right. Can everyone see my slides?
Yes.
Okay. Yeah. So now let's go with the topic of how we can apply DeText in language generation. So in this section, we'll use query autocompletion as an example to illustrate the usage of DeText in language generation. So query autocompletion is a task where for a given user input, we generate a list of candidate suggestions. For example, as you can see here, if a user input soft, then the query autocompletion will pop up with a list of candidate suggestions such as software engineer, software, or software testing for the users. Query autocompletion can greatly reduces the user's effort on the keystroke typing and also help the user formulate better queries that results in more desirable search results. And here is a typical workflow of a query auto-completion system. So for a given user input, it first goes through the candidate generation component, which generates a list of candidate suggestions. And then this list of candidate suggestions will be put into the ranking component. So for this ranking component, every suggestion will be assigned a score regarding its relevance to the user input. And currently, we use DeText in the ranking component, where with a optimized LSTM in language modeling. And in the future, we are planning to use DeText in a fully end-to-end and neural approach. So let's get back a little bit in the neural language modeling. So given a candidate suggestions for the user input, say research scientist, how do we model it in the neural language paradigm? So the basic idea is that we want to use the probability of the occurrence of these candidate suggestions. And you can see that this probability, if we take the logarithm of it, it can be represented as the sum of the conditional probability of each token. So let's look in more details. So for each token, we first extract the embeddings of this token and feed the embeddings into the LSTM cell one by one in sequence. And in the output of the LSTM cell, that's where we compute the conditional probabilities. We use both the embeddings of the next word, as you can see here, in the case of start of sentence token, we use the word research, and we also use the embeddings of all the words in the vocabulary to compute these conditional probabilities. And then we put these probabilities into the learning to rank layer. So more specifically, in the computation, as you can see on the left, on the right-hand side, in the dominator here, that's where we use all the embeddings in the vocabulary. And it's worth noticing that the usage of all embeddings in the vocabulary makes it very slow for the applications, say the real-time applications like query auto-completion. And that's where, that's the starting point of why we want to use a optimized language modeling LSTM encoder. And therefore, we try to approximate the denominator term. As you can see here, we use a learnable bias term to approximate the computation. The intuition behind is that first, we want to reduce the computational complexity to make it faster to run the text encoding and the probability computation. And second is that we still want to reserve the ranking effectiveness. And in addition, we also want to impose a length penalty. As you can see here, if you have more and more tokens in your query, this bias term will be multiplied with the length of the query, and which makes it, which puts more penalty on the long queries. And therefore, in the place where we have the vocabulary, we now replace it with a single term, the bias penalty. And then with this optimization, we make the language encoding faster. And here's the offline results. For now, we can just ignore the first two rows and focus on the row starting from the third row. Here we compare the unnormalized language modeling method, which is our optimized language modeling encoder, and the normalized language modeling is the one that use all embeddings from the vocabulary. And we can see here that our optimized language modeling approach achieves the similar performance as the normalized language approach, while maintains the language model, the superiority of language modeling over other neural embedding approach. And we also do our experiments compared to the traditional method, such as the frequency-based method. And we find that we have to combine these two methods to achieve the best performance. And this experiment is conducted in the publicly available America Online dataset. This table shows the latency results of our normalized language model versus other approaches. And as you can see here, if we adopt the normalized language model, which uses all information of all the vocabulary word at each step, it requires like 50 milliseconds for each query auto completion step. And it's very expensive and hardly tolerable for a real-time application. And while our normalized language approach is far more efficient. So combined with the approximate relevance results we've seen earlier, then it's a better choice than the normalized language modeling approach. So for online results, what we want to focus here is that, so we can see that with our normalized language model, we achieve better CTR, click-through rate in the pre-auto completion step. It also achieves results in better search experience. For example, if we apply it in job search, we increases the job views and the job apply clicks of the users. And this comparison is compared to a XGBoost model. So that's basically about the applications on language modeling. Now let's see how we can use DeText in practice. And in this section, we'll talk about the input, the training flow, and also the output of DeText. So the input of DeText, DeText accepts the input in the format of TF record. And the set of features supported by DeText are the text features, the ID features, and also the white features, or say the handcrafted features. And DeText recognizes the type of features with their name in the TF record. So for example, if you index, if you prefix the user text fields with user underscore, then DeText will recognize it as a user text field. Similar to that, if you prefix it with user ID, then it recognizes it as a user ID field. And since DeText is an end-to-end framework with great flexibility, we want to allow users to define their models through the model config. So as you can see here, we open a lot of model parameters in the DeText config. Users can config of course, the data input and output, and the vocab and the word embedding, and also features, metrics, loss, and also the network dimensions. As Xiaowei previously mentioned, you can configure the DeText MLP layers, CNN layers, BERT layers with the configurations parameters. And you can also use DeText for ranking or classification. And you can tune the optimization process regarding to the learning rate, training steps, and optimizer, etc. So how to use DeText in practice? So first you prepare the data with features in the DeText format. And then since DeText is open source, you can simply install DeText through the PyPI command. Just simply do pip install DeText. And it's worth noting that DeText is now in TF1, implemented in TF1, and the implementation in TF2 will go out soon. And so after you install DeText, you can create a DeText argument, say with the configs that we previously mentioned, through a simple command, say args equals DeText arg, and then you specify your argument with their corresponding value. And then you can just call the DeText main function and you import the run DeText function from the DeText package. And then with this command, you will trigger a training process, and then you'll get the resulting model and output. So what's the DeText output? First, you will have a hyperparameter logs, and also the logs during training, and also the logs during evaluation. In these logs, you will see the evaluation results per evaluation round, and you will also have the model have the best model regarding your specified evaluation metrics, and you will also have to save the protocol buff format DeText model. So in conclusion, we provide a deep NLP framework for ranking classification and language generation DeText. And this framework effectively encodes text information with high flexibility. It can be tuned for both search and recommender system. And this framework, we also explored efficient and scalable offline training and online deployment strategies. And here's our reference. You can refer to the GitHub link here for the open source implementations. And you can also refer to our paper for more details of the framework, the pre-understanding task, and our neural auto completion task. And we also provide a tutorial on KDD for more details. And that's all about DeText. All right, I think we are right on the time.
Great. I see we have quite more questions posted in the Q&A. Maybe we can go over some of them.
Okay. For the junk text, I see the junk text detection question still hanging here.
No, it's in the Q&A.
Oh, yeah, that's the Q&A, right? The one from the Neo Matrix 369.
Yeah, right.
With regards to detecting junk text from semi-readable text to highly readable, what features or traits we can detect or extract from the text to make our detecting and classification task easier or more accurate? I think this is related to the feature engineering. Yeah, so for handcrafted feature, I think I'm sure you could just Google it and find some experience shared by the online experts. But in the DeText case, the DeText framework will automatically generate or say extract the features within the framework as the process if previously seen that through the slides. So we extract the embeddings of the token, and then you do the semantics understanding within the framework, and then you specify it as a classification task, and then you can do it. For the more specific feature engineering, Wei Wei or Xiaowei, do we have anything to add?
Yeah, I think, so for example, for the query, So if I understand correctly, this is more about like the traditional feature or the wide feature feature engineering, right? So some of the examples can be, for example, if you have a lot of hashtags in your queries, then you can add such features like if query include hashtag, or you can also add, for example, like some like query tagging output probability like features to use for your classification task. I think it's more like task dependent.
Yeah, and if you have some say grammar parsing tools, then probably you can also use the information that such grammar parsing tools could not successfully parse the text. You can use such information to curate your features. Another question from the NeoMatrix 369, how does recommendation or completion work on mistyped or misspelled text, where correcting the word or words can open up a large graph of possibilities? Actually, I think that's a component that's called the spell correction that Wei talked about. So so first, you use the spell correction component, spell check component to correct the text, and to resolve the issue caused by the large graph of possibility. You only select the top, say top K, and you limit that K. You select the top K possible candidates for the word correction. So also by controlling that K, you can control your complexity. And another question from JR, do you incorporate user feedback into the auto-completion ranking? Actually, what do you mean the user feedback? I think, so for of course you can incorporate the user feedback. Like say you can have a session model which takes the previous keystroke feedback from user, whether the user delete the previous character or not, or depending on what they click. Yes, you can do that. I mean, in the DeText framework, of course, you can incorporate like whether the user click on it or delete, or say the user reshape their queries or continue typing. You can use this information and put it into as a feature. Actually, you can take it as a feature, right? You put this feature into your DeText model, and by doing this, you can incorporate the user feedback. Another question from JR, have you tried sampling to help with computing log PQ faster with a, I think what you're saying, yeah, so actually, if you want to try so sampling is a approach to solving this problem, that you have to have a specific sampling strategy, right? And in the case that you also want to incorporate the length penalty, then probably your sampling approach could not resolve the length penalty issue. So in this case, using our normalized language modeling, which introduces the bias term, could probably be a better approach. But of course, sampling is possible. And another question from me, will the slides or the link to the reference shared? I think that's related to.
Yeah, I think we need to talk with the company communication team. But anyway, this presentation is recorded, so all the information should be found in the video.
And also on the GitHub page, you will find our past tutorials and also CIKM paper for this DeText. So these publications are also available online, and pretty much cover the same information.
Right. We'll go with Gotham. Another question from Gotham. So does BERT, LSTM, CNN all share same embedding layer? Is it word piece tokenization for all? So first question, does they share the same embedding layer? Not sure if I understand it correctly. So in DeText, you specify which encoder you want to use, and then that embedding will be tuned together with the encoder. So I'm not sure like what would you mean exactly by the sharing, but one point I can think of is that the embedding layer is shared across all tokens when you're doing one specific task. That's the sharing that I can think of in one context. Another question is it word piece tokenization for all? Nope. It's actually user has a freedom to tokenize their tags for whatever tokenization, like whatever tokenization method they can find. So we open this freedom to the users, and users are free to choose whatever tokenization method they want to use. Another question from NeoMatrix 369. In your notebook for the text classification, it would help users learn more if you also had the output of each line in the notebook included. Actually, you can make a copy. I believe you can do that. So you can make a copy of the notebook. And the notebook is hosted in Google Colab, where everyone can have access to. So you can run it yourself and get the output. It's totally, we've tested the notebook, so it's runnable. So you can just make a copy and run it on your own.
Great. I think that's all. We are out of time, and also we cover all of the questions. That's great. Thanks a lot, everyone. Do you have anything to wrap up, conclude?
Yeah. Huiji, Wei, do you have anything to say?
Yeah, Huiji, do you have anything you need to add on before we end the meeting?
No, I think I think we pretty much covered all the things, and also thanks Bill for this great opportunity to share the work worldwide, and thanks everyone for attending. Yeah, so as I also mentioned earlier, we will have most of the reference posted on the GitHub page, and you can easily search those titles of papers, tutorials in Google, and also feel free to leave any questions, messages to us, and I think we have some. There are channels on GitHub. This week, we are also going to talk about this DeText paper in CIKM, and feel free to stop by. Yeah. So, and also really like build this vision to populate AI to everywhere across the world. This will help really help a lot for the industry. Yeah. Thanks.
Great. Great. Again, thanks a lot. Thanks.